Yeah. Okay, so I'll give you a little idea of, especially maybe the way I think about it, but it's like partly the way we all think about it, Kuramoto dynamics. It's a famous system of equations coming from engineering and engineering mathematics. Okay, so I have to see the screen. Okay, there's the...
Steve, you can stand behind the
what?
computer, then we can see you too.
I don't want to take his space.
Okay.
That's okay. You can see.
Okay, so this illustrates what we're doing. There's the authors in this project. It's a Kuramoto model from ordinary differential equations, written right below it, below the words Kuramoto model. And we're trying to, especially I'm emphasizing my view, but maybe the same with all of us. We're trying to see the structure of these solutions to this equation. So I call it global dynamics. We're trying to see the global dynamics of Kuramoto. That's the goal. So this is the general equation. So if you look at this at all carefully, you'll see it's invariant under a circle action of a rotation of all the thetas. So it defines something, first of all, on the torus in this picture of dimension n-dimensional torus. There's n variables. And if you take into account the circle invariance, you will get a quotient of m minus 1. So it looks the same. But it's now on the quotient of starting with m variables, or it's n here, not m. Yeah, n and m are the same. Okay, so on the quotient, we get one dimension less torus, taking into account circle invariance. So I'm going to focus on the four torus. M equals 5, and quotient on the 4 torus. So it's going to be a dynamics on the 4 torus, and we want to see the structure of this dynamics. And so that, at least in my view, means to find the description of all the solutions and how they fit together, all the solution curves. Okay. Maybe it's, okay, that's all right. This is induced function V. It went too fast. Okay. I say there's we lost something. There's a function V on the torus. In general, m plus 1, or m, in our case, 5 and then 4. So in the 4 torus, we have a function V. In all cases, we can represent Kuramoto equations, which are above in a much more simpler form. They will be the gradient or minus the gradient of this function V in every case. So V is a function now in the 4 torus, and gradient of V is exactly Kuramoto. This is the first step. Okay, so we can go to the next. These are all mixed up, but that's okay. Yeah, this one's kind of way out of order. So we want to look at the structure of this solution curves of Kuramoto relative to that V. I think the V was already passed, right? So we have the gradient of V introduced into this picture. Now we want to look at what's the important thing are the saddle points of dynamics, or the function V, more theoretic if you want. And especially my favorite way of looking at this is with theta, the theta i's going from 0 to 2 pi, not inclusive. So it's becoming like a big patch on the 2 torus, which is not the 2 torus as a torus anymore. It's sort of split up because the gradient dynamics is changing theta in one direction, so it can't be periodic. So it's increasing the function v with theta. And you get this picture. Well, I don't like this picture here, but if you look at the gradient of v, it's coming, the solutions for minus gradient v are coming down in this picture, and they go from the top, which is going to be a portion of the torus, which is what you call a Euclidean picture, because you take the theta i's going from 0 to 2 pi, not inclusive, because it's that way you can see things without the periodicity. So in this picture, with theta i's going from 0 to 2 pi, not inclusive, you put a patch over the whole torus. You get a patch. And that patch you can write down explicitly what happens and then analyze the solution curves in terms of how they fit together and the whole length of the solution curve in that patch. The patch, though, is still this Euclidean space, but it covers the torus. Okay, so, and you see in this picture here that I didn't like at this point, the solution curves for minus gradient are going sort of downhill towards 0 from close to the maximum of V. V is decreased to 0. And it starts, I like to start V slightly less than at 2 pi, because it's in this portion which is more Euclidean. Okay, so what's crucial here is the stable manifold structure of the saddle points. Almost everything can be described in terms of saddle points of that function. And when I say saddle points, I mean to include the minimum. It's not strictly a saddle point, but the saddle points plus the minimum gives the structure. Okay, so we can go further. Then we have a diagram that's really...
You want the table?
Yeah, I want the table. So this table had a big role. Indika made the table. So he's listing all the saddles here, including the minimum. So,
yeah, I think you can make it bigger, Indika.
Yeah, make it bigger.
This computer.
With a plus minus that you have on top.
What's that?
Plus, there is a plus, minus
Top
plus
of
on
the
top.
back, shift plus, shift
Then
minus.
increase it.
Yeah.
So we're looking at, so we're looking at 5 here, dimension 5, taking the quotient for m equals 5 to get a 4 torus. And this 4 torus, one thing can think of as very, very crudely is just eliminating that last 0 coordinate. That's a little crude, but it'll do for the moment. And so you have the first 4 coordinates there, and always the theta I are going between 0 and 2 pi, not inclusive. And these are the description of the, you might call the critical elements or the saddle points of V. So they determine so much of what's going on. And you see the index here is going to be the dimension of the unstable manifold. I don't think many of you may not know what not stable manifold theory. But the stable manifold theory is sort of a key to everything that we do. The stable manifolds are going to be cells attached to each of these points of order 1 or 2. And the saddle points are given here. Let's see, in one, yeah, so the saddle points, is there another slide?
No, it's
Yeah, in the template.
Oh, yeah, yeah, this template was never finished. Let's go to some templates. So we need templates. This template was never finished, but I can just point out what it needed. And that is a point here, which is pi 0, and on the side 0 pi, and then the center pi pi. The pi pi is coming from an index 2, so it has a two-dimensional unstable manifold, which fills up the whole interior here. The other stable manifolds are on the coordinates here, which fill the one-dimensional space, starting at a point here, pi 0, and it expands in both directions towards 0. Okay, and the same, similar for the sides. So you get a, so these are the templates, but you can fill this in. So this is expanding. The flow fills up the whole square. It looks like a square. Fills up the whole square, and these are the boundaries, which are circles. And this is a two-dimensional stable manifold. Unstable manifold at this point. And the stable manifolds emanate from this template. Their templates are 10 in number. There are 10 of those templates, and those are all two-dimensional tori. Then the one-dimensional tori are these circles. There's 5 of them. And you can figure out by combinatorics how they would fit together. And there's 1 0 0 0 0, which is a single one of index 0. Okay, so the one of index 0 is a four-dimensional stable manifold attached to that. That'd be like a big cube covering the torus, 4 torus. And this has got 10 of these and 5 each of these. Okay, so that's the starting point. Then we have to look at the stable manifolds. Some of you know stable and unstable manifolds. The unstable manifolds are all contained in the template.
Steve, microphone? Yeah.
Oh, okay. Thanks. Yeah, the unstable manifolds are all connected to one of these templates, one of the 10 templates. So here we have one-dimensional unstable manifold filling out this axis. And there are 5 of those circles, and they all fit together along the boundary. The 10 templates fit along the boundary. Okay, and that's all what I call the lower part of Kuramoto. That means all the V's less than or equal to around the middle dimension. And then the other part flows upwards from the templates towards the maximum, towards V equals 4 pi. Anyway, that's the picture. If you understand stable and unstable manifolds, then you get a much more solid picture of the dynamics. Finally, I would say the unstable manifolds are just like I described according to these templates. Stable manifolds emanate from the zeros here and there. And so the stable manifolds have a nice pattern. You start with the 4-dimensional stable manifold of the 0, 0, 0, 0. And embedded in that are the stable manifolds of the index 0, all those. And finally, for the center points index 2, you have stable manifolds all fitting in nicely to the 4-dimensional stable manifold of the whole object. And that gives the way that these stable manifolds sort of partition up the whole flow going in one direction, and the other direction is described by the templates, the bottom and the top. There's according to that table, there's nothing, no saddles or any other structure in the top part. This all flows up to 2 pi evenly. Anyway, that's the beginnings. We'll look at
Okay, Dr. Smale.
Now let somebody else take over, huh?
Yeah, I think I will give to Charles, but before I'm giving to Charles, I will tell you how we end up with this problem. So I have a slide. So it is not working, like something wrong. Can you help me? I need to see the screen and connect together. Oh, yeah. Yes, please.
Normal.
So can you? Yeah, sure. I have one slide to show. That's it. Then. Yes, this one.
So just hit, or go to the slideshow.
But this is, I can, this is not. Okay. So I want to mention this because everybody talk about Turing. So I think Dr. Smale and I started to think about this problem around 2015. Then this was this famous paper by Turing, 1952. The chemical basis of morphogenesis. And then, as Leon mentioned, so Dr. Smale touched that problem in 1976 in a book by Jerry Marsden. So the thing was, neither of them that time, so they were interested in cell-cell interactions. They both never knew that time the genome. In the cell, inside the cell, you have the nucleus, you have the genome. So the genome has 20,000 genes. That is your inheritance. So last maybe 10 years, we know that, we can see that inside your cell, where is your genome. So what Dr. Smale and I tried to do was try to bring the genome dynamics together with cell dynamics, try to define something called tissue function. So then we wrote a paper in 2017 on emergence of function from coordinated cell in a tissue. So I learned so much. I think I learned so much. I think I'm so grateful. I know Dr. Smale for a long time now. The way he thinks, as you said, perfection. And so I want to tell you that inside the nucleus is amazingly beautiful. So this is the way your genome is organized inside the nucleus. So my work, for my other work, my lab, I try to understand how the genome is organized inside the nucleus, any human cell. So we try to understand exactly going back to like Turing, that this is I adapted from your paper, Leon. 2 cells, then he wrote this kind of equations. But in ideal world, this inside the cell, you have 20,000 dimensional system, genes. But more than that, the entire genome is, if you take out the genome out from your nucleus, is 2 meters long. It's an amazingly beautiful system inside. So we thought of understanding how they interact into each other. So after that, our first paper, Dr. Smale got extremely interested in how the heart beating in unison. Your heart beating in unison. So we try to come up with a mathematical way to describe that one. So that's the way we end up with Kuramoto. And then Charles entered to this problem with us. And then Gregorio entered to this picture with us. So Dr. Smale and I have been Zooming and Skyping pretty much every day for many times. Then last 2 years, maybe 3 years, once a week we meet every Wednesday to thinking about this problem. So I will give it to Charles and Gregorio. They are thinking like a little bit differently, I think, this problem. So I am with Dr. Smale's side. We are thinking a little bit similar. I am following him, Dr. Smale's way of thinking. So Charles,
Okay, I'll say a few things.
yeah, we are writing a paper. I think two papers. I think one is I will write with Dr. Smale. I am already starting to outline that, the way we think this one. And then there's a mathematical paper, too, long paper with all four of us. Five of us.
Five.
Yeah, five.
One more.
One more.
Dan
One
Burns.
more. Dan Burns from
Dan
University of
Burns.
Michigan. Yeah.
So,
Okay, Charles. You want to connect this
you
one?
need to put your
Okay.
computer
Yeah.
on?
I'm going to need this briefly.
Yes.
Ready to go. Let's press it. I hope.
Just put it on top of
Is
you.
that okay?
Yeah.
Okay, it's not going to slide off.
Well, let me move it. Good point.
Okay. Okay, I can just use this.
Dance. You. Okay. Dr. Smith, you come in. Oh, excuse me. Do you need to close it?
I need to be able to write on it.
Here, so you can see.
You can't see.
Yes, that tone. Okay, yes, I'm audible. Okay,
So where's the?
okay. So the equation for V was this. Now,
We need a better.
this is reducing, as Steve said, a problem which is originally on the 5 torus. So there's 5 variables on the circle. And reduced, because there's some symmetry in the problem, to a V on 4 torus, which we studied. So Steve described very well the situation where V is not near the maximum. The maximum is m squared over 2, where m is the original dimension, 5, in the case of, we're looking, this is a problem, Kuramoto problem, is usually with thousands of dimensions. But we wanted to understand that, exactly as Steve said, the global picture. Just sort of thinking of it as an independent problem on its own. And I should have said, the V, which is used in the standard Kuramoto with zillions of variables, has constants. An additional constant in front, and the fact that these are perfectly symmetric, not perfectly symmetric. So this is a great simplification of what's ordinarily called Kuramoto. Anyway, Steve has described what happens, what the picture is like with these templates on the lower part of the V. So the Kuramoto flow is the negative gradient of V. So that's what we're studying, this flow. And as Steve said, it's got a finite number of critical points when you are at values below the maximum. But when you're at the maximum, you have a set. So that's the points on the 4 torus where the value is equal to m squared over 2. And that's an interesting set. It's a two-manifold, which you figure out just using the implicit function theorem and the equations and messing around. And you can see it a bit because each point in the 4 torus, it's a 4 tuple and as he was saying, you would like theta 1 to be positive as an angle, and then theta 2 bigger, theta 3 bigger, theta 4 bigger but not 2 pi. So if you were making a picture of it, you'd say here's 0, theta 1, theta 2, theta 3, theta 4 maybe. That would be a way to represent an element of T4 by thinking of these dots on the circle. When you're talking about points which are in Vmax, they take a special form. For instance, if they're equally spaced, then you're at a point in Vmax. But there are other situations where you're also in Vmax. Enough. So that's sort of a description of Vmax in terms of a picture. And as I said, with the implicit function theorem, you can see that this Vmax set is actually a two-manifold. You can also see that each point in the each capital theta, which belongs to Vmax, I shouldn't have said each point. Most of the points have these separate theta 1 is positive, theta 2 is bigger than theta 3, and so on. But any permutation of them also satisfies the equation. The equation is symmetric under permutation. And so you say, well, each set of thetas with this property, 1 less than 2 less than 3 less than 4, it's a sort of a region in Vmax. And you can see, you can prove it again, implicit function theorem, that it's actually a pentagon, where the sides of the pentagon are where you have some equality between the various angles. So this might be theta 1 equals theta 2, but otherwise different. So you say, well, how many regions like this are there? The same as the number of permutations, 24. So you say, okay, 24 pentagons form Vmax. What about the edges? So you want to count things. How about the edges? Well, each pentagon has 5 edges, but you're double counting them because there's another pentagon over here. So how many edges do you have? 5 times 24 over 2, right? 30. So what am I about to do next? I've got the number of faces, the number of edges. How about the number of vertices? Well, each pentagon has 5 vertices, right? 24 of them. Now, how much is shared at each of the intersections? The intersections occur like this. The edges of the pentagon continue on into the next pentagon. So for each point, each vertex, you've got 4. Okay, so 5 times 24 divided by 4, 60.
Charles, maybe you can write here.
You're right. Now, let's see, if I called it E, E is the number of edges, right? How about the number of points, vertices? All right. So let's see, what do we have? 5 times 24 over 4. So I calculated it wrong, as usual. Let's try it again. Let's try it again. 24 of the faces. Yeah, that's right. That's there's an eraser, I bet. Yes. All right. So
Is that what you were worried about?
24, and the other is 60. All right. Now, so Euler characteristic. That's how you see what kind of a surface you've got. All right, so you've got F plus,
Minus.
well, okay, it's
F plus
Shouldn't be
F.
30.
F minus E.
something's moving. Okay, it's the board, not me. All right, F
Minus E.
plus V minus E. There we go. All right, so that's F plus E. It's minus 6. All right, I hope. Minus 6, you want to know what the Euler that's the Euler characteristic. So it says you've got a two-dimensional manifold, Euler characteristic minus 6. It's a four-handled sphere or four-handled or four-holed torus. Right?
I am confused. B is not 60, it should be 30. Because you said 24, which I agree with you. You said 24. B should be 30, if I'm not mistaken.
I probably got them backwards.
Yes. Because
I got them backwards.
24 divided by 6 is...
So these are the discussions every Wednesday.
Yeah.
6 times 5.
So Kuramoto model itself a beautiful simple equation. We make so complicated sometimes.
Right. Anyway, the point
Everybody
is,
should
the
know
point is,
mathematicians aren't good at arithmetic.
right. I'm a prime example.
If you're ever
All
out to
right.
dinner.
But this says what the topology of the Vmax is. And here is a picture of it. Now,
So-
if I plug this in
Yes.
and press this, it might happen.
Yes.
Okay, let me move this.
Yeah.
This was made by my son, who's a graphic artist. It's good to have a son like that. Anyway, so that's, you see the four handles. You can spin if you wanted to. Anyway, so that's the object, which is in fact invariant, in fact under the Kuramoto flow. In fact, all points of it are fixed by the Kuramoto flow because it's the maximum of the function. So the gradient is 0 up there. And it's got better properties than that. Okay, so enough of the pictures. I think that will turn it off. Yes, good. And I have a little more to say about it, but not much.
Charles, we have another maybe 10 minutes.
Okay, so,
Yeah, including Gregorio.
right.
Yeah.
Including
And there's some food after that. Yeah.
Where's the eraser?
That's
Okay. That's fine. Okay, so we have the setup. The bottom part of the four torus has the critical points. The top part is the Vmax. And we would like to understand what the trajectories are doing as you follow them backwards up to the maximum. How do these stable and unstable manifolds imprint themselves on Vmax? And that's partly solved by us, but not entirely. But what's interesting is, to me, that Vmax is an invariant manifold by a smooth flow, and it is normally hyperbolic, meaning that Vmax is two-dimensional. It has a normal bundle of disks in two-dimensional disks in T4, which is invariant. It's normally hyperbolic because you can calculate what the derivative of the, that is to say what the Hessian is, of the gradient function. It's normally hyperbolic, which means that under perturbation of the equation, it remains. If you have a V tilde very close to V, you have the whole situation over again. You have this Vmax, and it's still there. You have the rest of the flow. You've still got the critical points. You've still got the minimum. You've still got the stable manifolds. They're all in roughly the same position they were before. So the fact that we simplified the original Kuramoto system, which has lots of other constants and things, didn't matter in terms of the topology. That's all I have to say.
Oh, is this not a HDMI? Is this one?
Yeah.
It's the wrong. I think we have the wrong.
That's a USB-C.
Yes, we have the wrong one. The correct is this one.
That's?
HDMI.
Oh, I see. Yeah, I don't have that.
Okay, I have it.
Okay.
Just a second.
Gregorio,
Yes.
maybe because of the time,
Yes, I just need to find out the for the connector, which is somewhere in here.
yeah, let's.
So I was going to show some pictures.
Do you all collaborate?
So I was just going to show the pictures. So
But he's in New York.
Maybe we can show the
Yeah, they do it
what you
on
printed.
Zoom.
I have a picture here that is quite easy to have.
You allow it talking together. Yeah, Wednesday,
So you have a weekly schedule or something like that? Do you have a regular schedule where you
They
meet?
do, yeah, every Wednesday.
Every
So, they're in Berkeley, North Michigan, and
Okay.
Found it.
Oh, good.
Okay, so just a second.
Let me see, I didn't know that.
So a lot of things have been already said.
PhD.
You
So,
student
I need the microphone. So,
I have one here. It's okay.
from Berkeley.
So we heard a lot today about how AI and technology needs math. But I think we are seeing a little picture of how math needs some technology. Right? A little bit the opposite. But this is how math gets done. It's like, often you just see the finished product. This is in action.
Okay, so
Okay,
is it on?
Gregorio.
I can start. So it's quite late. I am over time. So I will not repeat what the others have said. I will not say many things. I want just to show you a few pictures on Kuramoto dynamics. Before I continue, Dan Burns is part of our Zoom team. He has been participating here. So let's jump a few slides. And just to remind you, this is important. We start in dimension m. With a torus of dimension m, there are m angles. Now, there are 3 different group actions which make things quite confusing because those are 3 actions. One of them is the discrete action, just changing a coordinate by 2 pi. The other is the diagonal action. And the third one are the permutations. Both keep the potential, but here is what gets things confusing. The vector field is invariant by the 2 first actions and is equivariant by the other ones, means that if you make a permutation, the vector fields get the same permutation. Now let's get to the interesting pictures. One of the first conjectures for the low potential regime for small potential was that locally Kuramoto dynamic would look like perfect Morse. This is perfect Morse. This is a product of, here you have a repeller and the attractor. This is modulo 2 pi. And you could have this in dimension up to anything below m over 2. You have those flat structures that are templates. They are indexed by subsets of coordinates, and all the other coordinates are 0. This is flat. Now, this is what actually happens. So this is a subspace of dimension 2, a template, when the dimension is 5. It looks like different, but those 2 vector fields are topologically conjugate. So in some sense, the dynamics is qualitatively the same, although the picture looks a little different. Let's increase the dimension. And again, so you see in the middle, we have a saddle of index 2. The repelling direction is 2. And the lines in red are the stable manifolds of the saddles here in the middle of the sides. This picture is all modulo 2 pi on both directions. So let's keep increasing the direction, and behold, let's go to almost infinity. We get something that really looks like perfect Morse. Now let's go to the high potential. So there is nothing between the middle of the potential and the top. And on the top there is that source that is sometimes a manifold, sometimes it has singularities. It depends on the parity of m. So here you see the situation for m equals 4. So you can see this in dimension 3. Vmax is a union of 6 half of circles. They meet at 3 points, and important, where they meet orthogonally because of the action of the permutation group. And you are seeing everything modulo 2 pi in the 3 directions. This box is not orthogonal. This is important. In order to display Vmax geometrically with the right angles, I need here to put the real, the true angle that arises when we project from Rn into the counter diagonal. Now, let's go to Vmax for dimension 5. So this is the atlas. For every ordering, we got a pentagon. And this is a two-handle structure that relates each ordering to each one of the pentagons. Now, there is another way to see Vmax. So this is another interesting picture. So Vmax can be seen as a quotient of the Poincaré plane. Why did I look at Poincaré plane? Very simple. We know that the pentagons are orthogonal because always of the symmetry action. So where can we find a regular pentagon, an orthogonal regular pentagon in Poincaré plane? So now trouble is there are 24 pentagons and the 5-fold symmetry. So in order to get the quotient, I had to divide one of the pentagons in 5 and accordingly the other. So we have those 5 parts, and this is a fundamental domain of Vmax. So what you see here is how the other pieces glue. For instance, the purple one glues here and the green, and also here, 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 and so on. So this is a global picture of Vmax. And before finishing, I was visiting Indika. So I visited Rajapakse labs. We were able to print something that was then improved. Vmax. So this is a model of Vmax. And happy birthday, Steve. And there is a small one also. So, maybe if you want to see, I can pass around.
Dr. Smale, this is the small one.
So we don't know what to do with that yet. Yes, yes.
Okay.
Thank you,
so-
Gregorio.
You're welcome.
So, yeah,
Okay, well, I think we're,
we are done.
I think we're done. I'm not sure if we're done, but this is at the end of this part of the program. As I understand, there's a reception outside.
A reception outside,
But I
yeah.
want to thank everybody for coming here. I thought, I mean, I gave a talk, but I really loved hearing everybody else's talks here, and especially this afternoon, hearing other parts of Steve's work, which some of us are not as familiar with. So thank you. Thank you very much. I want to thank Michael Xuan for helping support this whole endeavor. Indika for taking the lead the past few weeks. Well, and Mike. And so happy that Mike is here. That's, you know, one of the very best things about this conference to see you here, Mike. You might have mentioned that for a number of months he was touch and go. So happy to have our friends from Brazil, Gisela, from Michigan, from all over here. And so let's just enjoy the last half hour or so outside. You want to say some words, Michael?
Yeah, I will add one more thing, that just beginning this month, we have also space in Shanghai for Smale Institute, which has more than 10,000 feet, you know. So everyone want to visit, organize activity, and visit, you know, and have workshop, and yeah, very welcome to use it. And it has office space and meeting rooms, and you can use for weeks, months, you know. So it's available to all, you know. I mean, the friends, the community of Smale Institute. Yeah.
So
Yeah, we
last,
have been certainly also having this virtual conference in the last few years.
Every
mainly
year for
organized
Steve.
by Indika.
For Steve's
So, and
birthday, yeah.
so
But also I want to thank the panel, this final panel here, Steve and your colleagues, Charles, Gregorio, Indika. for sort of illuminating us on the Kuramoto equations and how they're starting to be solved in this sort of more qualitative way in terms of these wonderful pictures. I don't know where the other piece is. I have a tiny one here. Somebody want to see it? Okay, and you want to end up? Okay.
Yeah, I want to end. There's a reception now organized by the Dr. Smale's mineral friends. And Rob Lewinsky, Stuart Swilsky, Sander Fuse, and Jean Myron. So please, let's go outside.
And also,